morning. We're going to talk about the SPICE DSK system now. This is one of my favorite topics. This is the digital shape kernel system. So I'll give you a quick overview, talk about the supported representations, tell you what's in the N66 version, present the APIs, give you one example of an API, and then briefly go over the DSK utility programs, DSK concepts, and how to write and use DSK files. So the DSK subsystem is meant to enable SPICE applications to conveniently make use of surface shape, topographic data, and geometry computations. It's also a format for transmission and archival of surface shape data. The system consists of SPICE software, DSK file format specifications, and documentation. It handles two representations of shape data, a tessellated plate model and a digital elevation model. But development of the digital elevation model portion is not complete, and there isn't any support for it in the N66 toolkit. DSK supplements the triaxial ellipsoid shape model already supported by SPICE. Plate model representation represents the surface as a collection of triangular plates. It's more flexible than the digital elevation model. Any arbitrary 3D surface can be modeled. Surface could be a complicated shape with multiple surface points having the same latitude and longitude. For example, a dumbbell-shaped asteroid, caves, arches. Comet CG is an ideal real-life example. It's less efficient than a digital elevation model of similar resolution in terms of storage and computational speed. Because the plate model representation does support arbitrary shapes, it doesn't support nearly as efficient data lookup, although it does have fairly extensive indexing capability. So digital elevation models map longitude and latitude to elevation. Elevation of a surface point can be defined as the distance from the origin to a body fixed reference frame. Distance from the origin of a body fixed reference frame. Or it can be defined as the height above a reference ellipsoid. Here's an example of a rendering made from a digital elevation model. Okay, so as we said, only the Type 2 DSKs are all we have supported right now in the N66 toolkit. Type 4 digital elevation model support will be added in the future version, but it won't be the next SPICE version. It will be one after that. Few DSK features. DSKs, like SPKs, can be multiple segment, and DSK file sets can span multiple files. Up to 5,000 DSK files can be loaded simultaneously. It supports runtime data translation like SPK does. So you've heard that you can read a non-native SPK file although you cannot write to one. You can read a big end-to-end SPK on a little endian machine and vice versa. That's also true for DSK. Now, some people may have been using the alpha DSK toolkit. It's actually been in use for over 10 years. And that toolkit did not support the runtime translation capability, so this is new in N66. So here are the APIs that we support, APIs that are DSK enabled, so to speak, at the high level. There are kernel loading and unload routines, which already existed in SPICE, and now have simply been extended to work with DSKs. Geometry routines, most of these, a large fraction of these already existed in SPICE and have been enabled to work with DSKs as well. So for example, surface intercept, ray surface intercept point now is extended to work with DSK, and then there are these two DSK specific routines. This one is vectorized. This one is meant to work with a sequence of rays, and this one works with a single ray. Southern observer points, a solar point, both can be used with DSK target body shapes. Illumination angles at surface point, all of these routines can work with a DSK shape. Longitude, latitude grid to surface points, this works with DSK shape. Find occultation state at a given time. This works for a combination of a DSK shape and a point target. Find an occultation or transit of a point target behind or across the DSK shape, difficult. So this was a routine that works with both ellipsoids and DSKs. So does this, by the way. Generate limb points. This is a fairly complicated routine. It is brand new in N66. It does work with ellipsoids or DSKs, and generate terminator points. Also new in N66. Another new routine, compute outward normal to surface point. This works with DSK shapes or with ellipsoids. There are routines for creating DSK files from within a program. DSK open, write segment data, close, and helper routines that create inputs that are needed by this writer routine. There are also DSK summary routines that tell you what objects you have data for in a DSK file, DSK obj and DSK surf. This tells you what surfaces are available for a given object. In the next several charts, we'll give some graphic depictions of high-level geometry APIs. This is the surface intercept routine, syncept, and here we have the observer location. We have a target represented as a plate model, an input ray that's provided by the user, and what this routine will do is if there is an intersection, you can see that there can be multiple intersections. If there is an intersection, the one closest to the observer is the one that will be returned by this routine. One thing to note about this is that the plates of a DSK shape model have an implied outward normal direction, and the array has to hit the side where the outward normal is pointing out in order to be considered an intercept. So if a array hits the back of a plate, that's not considered to be an intersection. Okay. Sub-observer point, there are two ways of defining a sub-observer point. One is to take a ray that points from the observer to the center of the object, and then that ray is intersected with the surface. Another is to take the array that goes from the observer to the nearest point on the object's reference ellipsoid, that defines the direction, and then take the intercept of that ray with the surface. By the way, the subsolar point routine works in a similar way. Illumination angles, so we have an outward normal vector here on a particular plate, and the illumination angles that are familiar are defined relative to that outward normal vector. The illumF routine also returns flags, observer visibility flag and an illumination source visibility flag that indicate whether the line of sight to the observer is blocked or not, whether the line of sight to the illumination source is blocked or not. The illumination source is treated as a point. And so you can see that with a very irregular shape, a non-convex shape specifically, that you can have an emission angle that's less than 90 degrees, but still not have the point visible because there could be a self-occultation. Similarly, the incidence angle could be less than 90 degrees, and yet the point might not be illuminated. Plate model limb. The idea here is that there's an observer location, there's a target, there's a ray from the observer to the target body center, and then there is a half plane that is selected by the user. Actually, the user specifies a set of one or more half planes using inputs to the routine. And in each half plane, it is possible to find a tangent ray lying in that half plane, tangent ray emanating from the observer location and tangent to the surface. So iterating over the set of half planes the user defines gives you a set of limb points. So I guess we've simplified this in the online version of this tutorial. We point out that for very irregular shapes, it's possible to have multiple tangents in a single half plane. In fact, that even happens for some Rosetta observations of Comet CG. And the limb point routine will find all of those tangencies. Terminator, it's a similar idea. We have user specified half plane and we have array that is tangent to the illumination source and tangent to the target, and we produce a point of tangency here, which is a terminator point. This is what we call the umbral terminator. This is, if we had a smooth shaped target, the points on the far side of the umbral terminator would be in complete darkness. They wouldn't see any illumination from the sun center in this case. And there's also an option to compute a penumbral terminator, which computes the boundary of the points that see sun illumination. So here's an API example. Here's where we call synset, and we see that actually the inputs are not changed from the N66 version, which is good because we maintain backward compatibility. This method string, however, contains some new items other than as opposed to what we supported before. In previous versions of Spice, method was just set to ellipsoid, and in fact, we still do that to model the target body shape using its reference ellipsoid. However, if we want to model the target body as a DSK, the simplest input that we use for method is DSK/unprioritized. And I actually will not go into much detail about what unprioritized means. It means that if there are multiple DSK data sources that all contribute, that can contribute data, unlike in the SPK or CK case, there's not a concept of a highest priority one being used. All of the DSK data available will be considered in the computation. But if you have multiple versions of the surface loaded, and you want to use only a selected one, which would typically be the case if you have multiple versions loaded. When I say multiple versions, for example, you want to have a very high resolution version and a low resolution version that's suitable for rapid computation. Then you can specify one or more surfaces that are the ones to be used for computation using this surfaces list. So we have this /surfaces equals and then surface name or ID. But this is all discussed in detail in the API documentation for synset. So these are just the inputs and outputs. Again, these are described in API documentation. Okay, utility programs that work with DSKs. Make DSK is the one utility we have for creating a DSK file. It creates a DSK file containing a single type 2 segment, and it can accept a variety of inputs, all in text file format and along with a command file that specifies how the format of the input data file. And one thing that has been added versus the alpha DSK version is that in N66, the main DSK program supports height grids. You can export DSK data to text file formats using DSK EXP. This is also new in N66. It writes data from type 2 segments to one or more text files, support simple output formats such as OBJ. Now this is extremely important because you might not wish to actually use the DSK interfaces in Spice with your DSK data. You might want to simply export that data to a format that you already have software to use. Since DSK is a binary file format, it would be very inconvenient for you if you receive data in a DSK format, but that's not the format you want. So we give you this way of exporting the data so you can get at it directly and then manipulate it as you wish. DSK Brief is a program for summarizing DSK files. This can summarize one or more files together. It can show coverage gaps if you have incomplete coverage for a surface. And it can combine it can give you a summary that shows the combined coverage of multiple segments or multiple files. There's a utility for merging DSK files, DLA-cat. You can concatenate segments from multiple files into a single DSK file. And the existing routines for transforming binary architectures to expr, to bin, and bingo all do work on DSK files. Comment, which is already present in all the Spice Toolkit versions preceding N66, also writes the comment area of the DSK file. So a few DSK concepts. Surface is a new concept that hasn't existed in Spice prior to N66. Unlike the C kernel files and SPK files that have either a body ID or reference frame class ID. There are two IDs in a DSK segment. The first one is central body, which is similar to what you'd see in an SDK file. But then there's a second ID, which is a surface ID. And the reason for this is that this allows you to associate multiple surfaces with a given body and use them very conveniently in a program that's using multiple DSK files. Now with SVK, if you want to use multiple versions of a trajectory for a given body, you have to actually load and unload the file. So if you want to switch from one trajectory to the other, at a minimum you have to load the second file. You might have to unload depending on what you're doing, you might want to unload the first file first and then load the second file. Then if you want to switch back to the first file, you either have to load it again or unload the second one and then load it. With DSK, you don't have to do that. You can load all the files you want with different versions. And again, a typical application would be to have both high and low resolution versions of the surface, or maybe versions at multiple resolutions, more than two distinct resolutions. But you want to use them for different things, and using the surfaces allows you to say in a particular computation which surface to use for that computation. You don't have to load and unload DSKs to accomplish that. Data class, this is a hook to differentiate different kinds of data for different applications. It's a distinct concept from data type. And the data classes exist geometric characteristics of surface data. Class 1, shape is a single valued function of domain coordinates. Example for latitudinal coordinates, if every ray emanating from the origin of the body fixed reference frame associated with the body passes through the surface just once, that would be a class 1 shape. So Comet CG is an example of a shape that is not class 1. Such surfaces could not have cliffs or caves, and digital elevation models can represent class 1 surfaces. Class 2 is arbitrary shape, not required to be convex, closed, or connected. So you could have two disjoint boxes as a class 2. That would be a valid class 2 surface. You could have surfaces that don't bound in interior. That could be a valid class 2 surface. So plate models are the only DSK data type that can be used with class 2. And right now, you can have class 1 or class 2, but the only data type that's supported is type 2. Okay, kernel priority. So right now, kernel priority is not a concept that's used in DSK, but it may be in the future. And it would only be applicable for class 1 surfaces. That's the only kind of surface for which it looks like priority can really make sense. There's also the idea of coordinate systems associated with segments. So we support latitudinal coordinates, planeto-detic coordinates, and Cartesian coordinates. Those can all be the coordinates that are used to describe the coverage range of a segment, and that coverage range information is part of the metadata in a segment, just as time bounds are the metadata in a C-kernel segment or an SVK segment. And there's a concept of coverage. The spatial coverage of a segment is a region of space within which the segment provides valid surface data. Now this is usually not a very problematic concept, but it could be for a shape that is extremely irregular or doesn't bound an interior and doesn't have an exterior either. So segment coverage it's a region of space within which the segment provides valid surface data. The segment can have data outside of that coverage region. You can have data that are used as a margin to make sure that round-off error doesn't prevent you from finding the data, and also to prevent gaps between data and adjacent segments. Segment coverage is characterized by 3 coordinate ranges, for example, min-max longitude, min-max latitude, min-max radius. Padding data can be I just said that, so we call this padding data provided outside the segment's coverage region to prevent there from being any gaps between the segments. Segment coverage is also, the concept of coverage also is used, is a little bit confusing, it's also used in a 2-dimensional sense in the DSK brief program. The DSK brief program just reports coverage in latitude and longitude or in X and Y for rectangular coordinates. Okay, for writing shape and orientation kernels, the make DSK program is the primary way of doing this, although one can also write programs that use the API routines in the SPICE toolkit. The inputs can be sets of plates. They can be, so here, list of plate model vertices and associated plates. That's one valid input. When digital elevation models are supported, lat-mon and height above whatsoever distance from center will be supported. And we have, so we're showing the extension of make DSK. Actually, this bottom sequence is the one that's supported right now. The top one is one which will be supported in the future. PCKs, this shows the construction of PCK, axis dimensions for triaxial ellipsoid. Using a text editor, this could be put into a PCK file. You could create a kernel variable assignment for body radii. And orientation information, some source of rotation state, polar deck, and prime meridian location can be put into a PCK file using a text editor. So these are these are data sets that would be created in a text PCK file. Okay, using shape and orientation kernels together. I guess I haven't gone over the metadata that are in DSK kernel. The online tutorial discusses that in detail, and the DSK required reading discusses that in detail. The DSKs have a reference frame associated with them. Just as with SPK files, the shape data wouldn't make any sense without some reference frame. And so the reference frame is included in the DSK metadata. And what is not included, but what is necessary for geometry computations is orientation of the bodies. So you need to know how bodies are oriented with respect to inertial space. So in most normal applications, although not all, DSKs are used in combination with PCK data so that the surface can be related to inertial space, and then can be related to an observer's location. So this is showing the general form of this, showing that you could have either a digital terrain model or a tessellated plate model. This provides a shape, PCK, with the orientation given by PCK can be used in combination to do geometry computations that require the relationship between the orientation of the body and inertial space. Okay. Just one sort of overview, what do we call this? One background comment about DSK. I think it would be a natural question as to why does SPICE have a DSK system? After all, there are great data systems that work with shape data already. A lot of these are highly evolved. The purpose is what we said in the first bullet on the first slide, which is that what we're trying to do here is make it easy to conveniently use shape data in SPICE computations. You think of this as improving the computations that you could do with an ellipsoid to now have a more accurate surface representation. You want to do the same computations in most cases, but you just want to model the surface more accurately. For example, if you want to know the spacecraft height above the surface, instead of computing the height above the reference ellipsoid, you now can compute the height above the actual surface using your DSKs. Okay, any questions? Yes?
So if you had a high resolution local DTM, I know it hasn't been released yet, but when it is released, if you have a DEM that's high resolution local area and then a low resolution global map, say, and you merge them, can it handle different resolutions, or would it sort of upscale everything to the high resolution format?
Well, what would happen without any further development of the kernel priority idea is that it would use those data together and then give you a mess. So the kernel priority, not only does DEM need to be supported, but the kernel priority idea needs to be supported as well. I think what you want to do normally is say that for any latitude and longitude where the high accuracy data are available, that's what we use.
Now, the boundaries between high and low accuracy models are going to be irregular and they have real spatial gaps, so that can be problematic. But if you're doing something like doing computations for native pointed geometry, it would work very well.